Welcome to this explainer. Today, we're going to break down a really fundamental concept in vector math, the scalar product.
All right, let's jump right in. We can add vectors, we can subtract them, but what about multiplying them? How do you even multiply two vectors? Well, it turns out there's actually more than one way to do it. And the first one we're going to look at is called the scalar product.
So here's what we've got on the agenda. We'll start with what is the scalar product? Then we'll hit the two key formulas you need to know. We'll cover some really important special cases, walk through some textbook examples, do some practice, and finally, tackle some real exam questions. All right, first things first. What even is the scalar product? What does it mean when we say we're going from two vectors down to just one single number? Okay, this is the most important thing to get your head around. When you add two vectors, you get another vector, right? But with the scalar product, sometimes called the dot product, you take two vectors and you get a single number, a scalar. And that one number is super useful. I mean, it's used in physics to calculate work, in computer graphics to figure out lighting. It's a big deal. Okay, so how do we actually calculate this thing? Well, you've got two main formulas in your toolbox. And which one you pick really just depends on what information you've been given in the problem. So here's the first one, the geometric formula. You can probably guess why it's called that. It uses the geometry, the angle between the vectors. All you do is take the length of vector A, multiply it by the length of vector B, and then multiply that by the cosine of the angle between them. Pretty straightforward when you have those pieces of info. And then we have the algebraic formula. This one's your go-to when you have the vector components. And it's so simple. You just multiply the x components together, the y components together, the z components together, and then just add up those three numbers. Honestly, it's usually way faster. Okay, now this is where things get really cool. Let's look at two special cases. What happens when your vectors are perfectly parallel or when they're perfectly perpendicular? These give us some awesome shortcuts. Just think back to that geometric formula for a second. If two vectors are parallel, what's the angle between them? 0, right? And what's the cosine of 0? It's 1. So the dot product is just their magnitudes multiplied together. But what if they're perpendicular? The angle is 90 degrees, and the cosine of 90 is 0. See where this is going? And that right there leads to probably the single most important shortcut you'll learn about the scalar product. If the dot product of two vectors is 0, it means they are perpendicular. That's it. This is a massive deal. It's a test you are going to use all the time. Okay, enough theory. Let's put this into practice. We're going to walk through a couple of examples straight from the textbook to see how all this stuff actually works. So for this first one, look what they give us. The lengths of the vectors and the angle between them, 45 degrees. This is screaming, use the geometric formula. So we just plug in the numbers. Magnitude of P times magnitude of Q times cosine of 45. And boom, there's our answer. All right, now they've flipped it on us. This time, we get the vectors in component form, and we have to find the angle. So how do we do that? Well, we kind of have to use both formulas. First, we use the easy algebraic way to get the dot product. Then, we find the magnitude of each vector. And finally, we just rearrange that geometric formula to get the angle by itself. Okay, this example is a classic. You'll see this kind of thing a lot. We need to find an angle inside a shape. Now, the trick here, the most important first step, is to figure out which vectors you need. For the angle OBA, we need the vectors that come from point B. So that's BA and BO. Once you've figured out those vectors, hey, the problem is exactly the same as the last one.
Okay, you've watched me do a few, now it's time to get our hands dirty. Let's tackle some problems from exercise 9C together. This is the best way to really make it stick.
So question 1 is a perfect warm-up. It's basically asking us, for each pair of vectors, are they perpendicular? And if they're not, what's the angle between them? So it's testing both our shortcut and the full method. And as you can see here, for parts A and C, when you calculate that dot product, you get 0. So bam, they're perpendicular. We're done. For part B, though, we get 12, so not perpendicular. That means we have to do the full calculation with the magnitudes and everything, and we end up with an angle of about 81.4 degrees.
Okay, you need to pay attention to this one because this type of question comes up all the time. They tell us two vectors are perpendicular, but one of them has an unknown component, A. Our job is to find what A is.
And the strategy is actually pretty simple. What do we know about perpendicular vectors? Their dot product is 0, so we just calculate the dot product using the components we have, including the a. That gives us an equation. We set that whole thing equal to 0, and then it's just basic algebra to solve for a. And in this case, a is 3.
All right, let's wrap this up by looking at some real exam-style questions. This is where we prove we've mastered this stuff.
Here's your absolute bread and butter exam question. They give you two vectors in component form, and they just say, find the angle. This is just a straight-up test of the process we've been practicing.
And we just follow the recipe, right? Step 1, find the scalar product. Step 2, find the magnitude of each vector. Step 3, plug all 3 of those numbers into that angle formula, then just hit inverse cosine on your calculator, and you've got your answer.
And for our last one, it's even simpler. Just find the dot product and check if the vectors are perpendicular. This is all about knowing that shortcut.
So we just do the math. 1 times 4 plus 2 times -5 plus 3 times 6. It all adds up to 12. Now, is 12 0? No. So we can say for sure these vectors are not perpendicular. That's it. Simple as that.
So let's circle back to the beginning. The whole reason we call this the scalar product is because the answer is always a scalar, a single number. But that probably gets you thinking, is there a way to multiply 2 vectors and get another vector as the answer? Well, there is, and that is a story for part 2.